Good afternoon, everyone. It is my pleasure to introduce the speakers of this talk. This is Yacine Achiakh and Alain Sirois. Yacine is the CEO and co-founder of Wisear, and Alain is the co-founder and CTO of the same company. So we're going to talk about brain-computer interfaces. Without further ado, Yacine, we have the floor.
Thank you very much, Ivan, for the introduction. Thank you for having us as well. So we are Wisear. We are a young startup, French startup, 3 years old. I am Yacine, I'm the co-founder and CEO. And Alain, maybe you want to quickly introduce yourself?
Yes, hi everyone. I'm Alain, the other co-founder and the CTO. Sorry I couldn't be here today, but I'm dialing in from France.
So this talk might be slightly different than the one you usually have because we are a startup. And so I think in order to understand the technical roadmap that we have, we're just going to spend some time at the beginning to explain a bit about our vision and like kind of the product approach we're trying to take because this is what's really driving the technical approach that we have also. The other thing that might be slightly different is that there are some components of what we do that we won't be able to fully disclose at the moment because they're not public yet. So we will mention them, not mention them, like we might show them on the slides, but they might have a little confidential around it. Ask questions if you want, we'll try to answer them. Yeah, the idea is not that we didn't think about it, it's more that we cannot share everything today.
That's perfectly fine. We're in public domain. Feel free to say I prefer not to disclose that. That's okay.
Totally. And so what we're going to talk about today is neural interfaces and kind of how we think these will impact the future generation of human-computer interfaces for the device we're wearing. So where we're coming from with Alain is that we do notice that today wearables are eating the world. What we see here is that if we think 30 years ago, we all have desktops with keyboards and mouse. Then we move towards smartphones and touchscreen. And more we're going towards devices that are like smartwatches, earphones, and hopefully tomorrow AR, VR headsets that we're going to be wearing on us all day long. What this means is that the traditional controls that we've been using, mostly requiring hands or voice, will not be sufficient to be able to enable the users to enjoy their device in any situation, wherever they are. I mean, if you think about it, like all the human-computer inputs we've been developing for the past 30 years have always been asking us to use our hands, which is also the most important, one of the most important part of our body. So we've been like taught how to press keys, punch a button, click to actually transfer our intent towards a gazillions of other devices that we're using. And we think that this was great for the past generation of device. We think we need to evolve towards something that is more natural and more internal to who we are and what we are. So that's what we're trying to build at Wisear. We're trying to build a neural interface that sits in your everyday devices, starting with earphones, wireless earphones specifically. And so what we're doing is that we're collecting the bioelectrical activity that's generated by your brain, your eyes, and your facial muscle. And then we have a sequence of signal processing and AI technology that we have patented, of course, that is transforming these inputs or these signals into controls for you. So these controls can be controlling play, pause on the music, answering a call, really whatever you want if we think about existing earphones use case. If we think about AR use case, it could be navigating through an app, navigating through a carousel of app and selecting the app that you want to open. And if we think, for instance, about industrial or enterprise use cases, it can be triggering an alert where in a situation where you cannot use your hands and where voice is hard to trigger because of the noise around you. So a little bit about us. What we're trying to build is an ecosystem of neural interface powered products that let every human enjoy high-speed, private, and accessible controls. And we will come back on these three things because we think these are key for the adoption of neural interfaces. So we are 3 years old. Over the past 3 years, we ran a few pilots with large XR makers and earphones OEMs. We amounted to total 3.5 million in funding. We are also backed by research, and what I mean by that is that we've been working very closely with the Ear EEG Center from the University of Aarhus in Denmark, and also with the INRIA in France, specifically with their BCI lab Fabien Lot over there is one of the advisors of the project. And finally, we have patents in the US and pending everywhere else. In terms of the team, so Alain and I, we both co-founded the company 3 years ago. We used to work together for a French company, French tech company, in AI product development. I was on the product management side, and Alain was on the data science side. Before that, he studied neurotechnology, so that's where the knowledge behind this brain tech comes from. And I studied business and also a little bit at UBC next door, so that you guys may know. And over the past 3 years, we grew the team to 13 people. We hired Camille from SoftBank to handle the hardware, and Enzo from Netatmo, which is one of the French leading IoT company, to lead our software and backend technology. And as you can see, most of the team is mostly ML scientists and engineer in general, so we're really, I would say, research and tech driven. These are just fun pictures for those of you that like to play with prototypes. So the team that I just mentioned before has been quite duty and like one of the most motivated people over the past 3 years to try out a lot of things, from wearing headsets that are bulky and can be painful after a few times, or to shave their head to try like new type of electrodes. So really we have like a very motivated team right here. And also a little bit of humble brag because we always need to do that as startup, you know, that's part of the game. We were listed as one of the most innovative products by a bunch of these great newspapers you see here, but specifically we got the Best of Innovation Awards this year at CES, along with another award for being one of the most accessible tech on the market, which is again something that we try to build in our DNA. So what are we actually building these days? Yeah, sorry, that's a bit too bright. I should put these ones in dark. So what we have at the moment, and this is the thing that we're going to be demoing to you during this presentation, we've spent the past year developing our demo kit. So our demo kit looks like this today. I don't know. Well, I mean, it's on the screen anyway. But our demo kit looks like this today. So it's basically, we try to be closer and closer to your regular AirPods form factor, with the goal of tomorrow building a product that is so close to what users are already wearing that they won't see any difference in the product they're wearing versus what they used to wear. And it will just be enhanced with our neural interface. This demo kit, we've been using it for a few things. One, to easily, try out our technology and test it in multiple environments, be it running, be it cycling, riding your motorbike, really whatever it is, any kind of challenging environment, and really getting out of the lab in terms of testing what we've been building. The second thing was to test like a train, or like collect more and more data, and to make sure that, well, we are able to cover all the corner cases that we have been like not working in the past few years. And finally, of course, to improve it. So understanding what doesn't work with the current shape and form of the device we have. We are also in the process of building a few SDKs or integration with more general ecosystem. The idea is to not only have a tech that works with our own demo app, but also be able to let any external developer community or any researcher really use our prototype for whatever internal testing they would like to do. And finally, we have our demo app. One of the things that we've learned along the way is that it's good to think about neural interfaces, but since these gestures are completely new to most users, there is one part that is very important, which is how do you learn that gesture to new user? How do you make sure that people grasp it and get it because they're not used to it? And so this is a core part of what we're building, like a core product part, being able to understand what's the fastest path to teach someone how to use a new gesture to control their everyday device, so their AR glasses, their laptop, their earphones, whatever it is. And the goal of this demo app is also to let people customize the interface to whatever controls they want. So if they want like that eyes controls to the X or Y or Z, this app is meant for to do that. So again, because this is going to be guiding the technical roadmap, I think it's good to just like spend 5 minutes talking about what are our product challenges, what are the key things that we need to solve if we want to move from having a product that works in the lab to having something that's being used by everyone everywhere. I think and we discussed this a little bit earlier, right? One of the key things that is required to ensure good user adoption is to make sure that you limit the friction of wearing the device. Is like a lot of the thinking, I think, about the past 20 years was that, oh yeah, if we build a great neural interface or a great BCI application, no matter what the device looks like, everyone will be wearing it. And that's very likely not going to happen. And like we have it on like other devices that we're wearing on us today, right? Like the smartwatches, they're not a fully new device. They're just the heritage of like us wearing watches for a long period of time. And like if you had come like a sleeve, that would have been very different. Same goes with like earphones. Wireless earphones, they're not just like appeared like that. They were like the X evolution of having headphones, then earphones wired, and like now we have wireless earphones. So we really think that one of the key things to ensure user adoption is to integrate the technology in a form factor and in a device that people are already wearing or close to what people are already wearing. And the same goes for AR glasses, right? They will not go in the consumer realm until they look like glasses or slightly bigger glasses. So we've been focusing, we've been focusing from the get-go on trying, these are just designs that we're aiming at, but we've been focusing on the get-go on how do we make sure that what we're building can sit into these kind of devices, and how do we make sure that the user, when we're testing it on them, they adopt it and they test it. So from the get-go, we've been testing out our technology, having this device being worn by user to get their feeling, their reaction to it. The second thing I think that is quite important is to be able to solve a real problem. And so the question, again, like when it comes to neural interface and BCI, is that a lot of the time, like, is being built with like a very like futuristic or important goal, or just trying to go after like some measurement of like emotions or anything like this. But we don't really focus on the actual problem and when people will really need that technology. And the thing is that if you think about neural interface, they always go in competition with existing interface, right? You're going to have a keyboard, you're going to have voice, you're going to have like other things that you can use, touchpad. You need to think about the way you build your product as when does it come obvious to use that versus other interface that you could use. And this happens in like what we could call situational disabilities, or places where you would not be able to use your hands as like a natural input or voice. This is like a very basic explainer that we've been sharing around, and like you guys may recognize the device that Claire is wearing on that video. Again, it's just meant to explain, but like one of the key use case we see as a first application for neural interface is, for instance, everything that's related to industrial or enterprise worker on the field, where both their hands are usually busy to do something, and voice is not always an option because of the noise around it. So in this case, what she's doing is like she's kind of controlling her HoloLens using some of the control that we've built to take a picture and send it to someone else without having the need to use voice or hands. Oh, okay, wonderful. What do I do now? Okay, cool. Nope. All right, cool. I think the other thing, wait, let's do it again. That's for the use case. So we say simplify user adoption, solve a real problem. And I think the last part is meet people expectation. What we mean by here is that if we were to build a device that's great, that solves a real problem, but that takes 7 seconds to trigger an action or to trigger a control, no one will use it, right? And that's one of the thing that like we tend also to forget when we say, oh yeah, I'm solving a real problem. So because I'm solving that problem, people will be able to wait for whatever, like controls to happen or anything else. But when I say people, we have been taught and trained over the past 30 years to have super instant reaction of all the interfaces that we're going to be using. And so one of the key things I think that we need to understand when we're building this new interface is how do we meet people's expectations? And we've listed these expectations as the 4 that you can see right here. I think one of the key things that needs to be understood is like in the world that we're living in right now, there is more and more requests for privacy. And what we mean by that is like people expect whatever interface that you're going to be building to be really private. That's what voice, for instance, is not really picking up in public spaces, because you don't want to be talking to your phone, or you don't want everyone to know what kind of message you want to send to your mom or your kids. So really privacy is key. And I think this is where neural interface can play a key role, because like you are building controls that by nature are not visible from the outside. So this privacy, we think, is something that is core to what we need to achieve and what we need to meet. The second thing, and we were talking about this earlier, is like speed. Again, we've been taught over the past 30 years to have very high speed controls. And so we are working actively to make sure that we drastically reduce the number of time or the amount of time that's needed between the moment you do the gesture till the moment it triggers a control. And this is kind of a key thing to put in your technical roadmap if you want to make sure that, again, these interfaces are accepted and adopted by people. The third one is accessibility. And again, I think like Microsoft has been doing quite a lot in that direction of the adaptive controller, for instance, on Xbox. And you see like more and more large group like Apple with their recent like advertising campaign around accessibility, showing that we are designing controls and like devices these days so that they are accessible by design. So what we mean by that is you don't want to be doing one version of your product for the healthy population and one version for the patients or the people with disabilities. You want to have one product that can be used by all. And I think that's also something that's we've been trying to bake in our design. And that's also why neural interface plays a good role here, because again, like no hand or limited hands mobility, it's okay. A very good or very strong French accent like me using a voice assistant, well, you don't get blocked. So really like accessibility is key and part of the expectations we need to solve to get adoption of these neural interfaces. And finally, and I think this one is too often overlooked, it's reliability. So most of the devices we use today, most of the interfaces we use today, they have very, very high precision, very, very high recall, right? And this is what we got used to. This is what we expect from any device we are using. And so it's quite funny to see that, for instance, when users are actually trying out a device, if they have more than 2 bad experiences with that device, they drop it and usually don't touch it for another 6 months. This is super important because if tomorrow we release a Wisear neural interface and like we don't manage to meet the standards that people are expecting, then basically, even though the technology is great, well, we never get adoption. And so here, like there are a few different metrics that you can use to assess how user would get there, because like precision and recall are great, but they're like really scientific metrics and not really metrics that you would be using to assess like user penability. And so what we've been really focusing on is the number of false positive per certain amount of time. So the very first threshold that we set for ourselves, and which was the voice threshold like 3-4 years ago, is 1 false positive per hour. And I think now we're aiming towards something that's even better than this. The target we're having is more like 1 false positive per 48 hours of usage. So not 48 hours, but like per 2 days of usage, which is what we've seen as the new standard in terms of like the number of like false positive that the user is willing to accept and still keep using the device. Now, if we talk, sorry, I've been talking a lot already. If you have any questions at any point of time, just raise your hand wherever you are online, IRL, and we'll be happy to take the questions. So how does that translate into our product roadmap? And then I will let Alain take over. So this is basically where we are at. So of course, there are a few different stack in what we're doing. There's the hardware part. We've talked about our demo kits that we've been building. The goal for the end of this year is to have a dev kit that's going to be more compact. Oops. That's going to be more compact, easier to use, more adapted to everyone, and also able to cover more capabilities. R&D-wise, so basically science-wise, as I said, like I think what we did over the past 2 years was developing these first facial muscle activity controls that we're going to be demoing to you afterwards, and that Alain will go further in details. The goal for this year, and these controls, we've brought them to what we would call product level. So they are ready to be integrated into any device. We also worked on the speed of these controls. So right now, I think for 2 out of the 3, we're below 1 second, which is pretty much the same as like you raising your hand and tapping your earphones or scrolling onto a pad for AR glasses. For the third one, we're still slightly above it. So we know 1 second is the mark we need to hit in order to get to user adoption. So that's why we put that we're still slower than current controls. But the goal is to match these speed by the end of this year and go faster than that afterwards. And so, yeah, as I said, 2022, muscular controls, facial muscle controls. 2023, and we're working on it right now. Again, I'll give you a quick demo afterwards. We have eyes activity-based controls that we're going to be working on, and that we want to bring to that same product level. And then 2024 onwards, there are a few other approaches that we're thinking about to expand the number of controls we are going to be able to provide the user through our neural interface. And these will rely not only on EOG and EMG, but also on the EEG we can capture from the ear. Then talking about the hardware and the product solving situation. I think
what we said is that it's good to build a new interface, it's good to build a technology that works. Then the question is like, where are you solving a real problem? What we see today as the main market for what we're building is augmented reality, mixed reality, basically all the devices that we're going to be wearing in front of our eyes and for which we're not going to have a keyboard to type on in order to control them, because we think this is where the situational disability will be the strongest. But if you think about this market for consumer is not ready yet. There is no kind of mainstream AR device that everyone's wearing, and we still don't know what it's going to look like. So what we're going to go with in terms of roadmap is start with where AR is already a big thing, which is industrial enterprise AR, like HoloLens has been doing it, like RealWear or Magic Leap also diving into, and provide external controls for these devices for when the user cannot use voice and when the user cannot use any kind of trackpad or hand tracking in front of them. And so that's where we see like the beachhead for where we're going, and that's where we're going to be generating the first product that we're going to be selling. And then later on, expand as augmented reality expand towards consumer AR or any type of other AR that would make sense. And now I'm going to stop talking and I'm going to give it to Alain. Alain, the floor is yours.
Hi again, everyone. Can you guys hear me well?
Yep.
Okay. All right, so we're going to switch to our tech. Again, quick disclaimer, I'm not going to be able to tell you everything we did. I'm going to try to go to as much detail as I can, but of course, there's still some things that I cannot really disclose at the moment. The way we're going to look at it is we're going to start with our device, so really the hardware part, and I'm going to dig especially 3 different topics, the sensors, the analog front end, and the way we deal with electromagnetic interference. And in the second part, we're going to zoom a little bit more on the software side, especially the way we collect data, process it, and train a model. In that part, I'm going to just stick to like big principles without going too much into the details, but I hope still it can be useful maybe to you as well. Doing this like quick overview on everything we've been trying and everything we kind of isolated as the approaches with the most potential. Okay, so our device, and we're going to start with the sensors. So as you probably all know, the role of the sensors is to collect bioelectrical signals, which means converting the ionic currents that come from either your muscle activity, your eyes movement, or your brain activity. Your head is full of ions. This is what carries the currents. And we place electrodes on your skin, and especially in our case, within your ears, that convert those ionic currents into electronic currents. The few constraints we need to operate with when choosing or designing those electrodes are, first of all, the signal-to-noise ratio. We want to make the electrode skin impedance as low as possible. And we also want to ensure that there is not too much of an impedance mismatch between the electrodes. We'll get back on this afterwards. And also, when you're trying to build either like a consumer or an enterprise product, but something that you want to sell, cost is definitely an issue. Meaning that even if you have the best signal with some electrodes that cost $100 a piece, it's probably not the ones that you're going to be using in your final device. Biocompatibility is quite obvious. You wear those electrodes for quite a while, especially for us in areas that are quite sensitive, like the ears. So it needs to like pass all the biocompatibility tests. And comfort as well. You wear them like all day long. You want to have something as comfortable as regular earbuds in our case. Cleanability is both a question of hygiene and also, in the case of the ears, of signal quality, because you want to make sure that your electrodes stay clean to maximize, to minimize the impedance and maximize the SNR overall. Now let's zoom a little bit on the state of the art of what exists today. So you have different families of materials, right? The metals is definitely the most famous one, the one that people go to in the first place. There are all varieties of electrodes. Silver electrodes are usually the most popular. They are definitely the ones that give you the best kind of signal. Here I put a picture of an electrode designed by the EEG Center in Aarhus, Denmark, a lab that we work closely with. So it's actually a very tiny electrode you're going to see on the next slide, made in that case of a coating of iridium oxide, which gives very good results. But again, this is also a very expensive electrode, so for our case, we had to dismiss it from the beginning. Another family of materials is what we call the composite polymers. So it's basically a plastic or PDMS that is a non-conductive material that we will dope with conductors. It can be carbon black, it can be carbon nanotubes, it can be silver particles, whatever, to make it conductive. So you'll see this is the material we use. I mean, this is a version of the material we use. There are also, again, varieties of such materials. Usually their conductivity is a bit less than the metal electrodes, but on the other side, the comfort is usually a bit better. They're easier to clean and they are way cheaper as well. Then two other categories that are a bit less popular, I would say. First, there is what we call the intrinsically conductive polymers. So those are polymers that are conductive by design, and the most famous example is P.PSS. So you can see on the picture 3, it's actually kind of an ink that has been used to do tattoo electrodes on the scalp of that person. So it can actually unlock some new potentials of making electrodes, and why not making electrodes that stick to the skin for actually a few days, even a few months in the future, unlocking some different kind of devices to put on the market at some point. And finally, capacitive electrodes. So it's usually the one that we don't try that much. The idea is that they are very vulnerable to any kind of motion artifacts. On the bright side, they also don't require, they don't carry the conductors directly. So it's a capacitive effect. So they don't need as good of a contact with the skin as with the other electrodes. So for some cases, it can be interesting. Now, if we look at other dimensions of the choice of electrodes, the shape and the size are very important. The contact area is directly correlated to the impedance. So if you can afford having a bigger contact area, it's going to decrease the overall impedance, and also the contact stability, because you want to avoid having artifacts and avoid having like an impedance shift along the way. The placement of the electrodes, quite important. Maximizing the distance between the electrode is definitely key to improve the SNR. It's directly correlated as well. And also the way to place the electrodes like might be a way to be able to make sure that the placement is generalizable between subjects, especially if there are contact areas that are good across people and some contact areas that are very specific to certain people. So you want to avoid those points. And again, if you can afford it.
There is a question from the audience. Andrzej, can you ask your question by voice?
This is
yes.
Go ahead.
But
I think we don't hear him here.
And
can you hear him?
No, but he can.
Impedance being an important aspect. Does the presence of earwax have an impact?
Okay, Andrzej, we cannot hear you. So the question is question regarding it's in the chat. Question regarding the cleanliness. You mentioned that you want to increase impedance. Does the presence of fat in earwax actually help you?
So we want to decrease impedance as much as possible. Earwax is increasing the impedance. So earwax is not good for the quality of the contact. On the other hand, sweat is usually pretty good.
Okay. Please continue.
Okay. As I was saying, the number of electrodes is also key. So if you can afford to have many different electrodes, it's actually possible to try to find the right or the best combination for each subject. That's, for example, what you see on the picture on the top left, picture A. So this is the same group, Ear EEG Center in Aarhus, that have been using the small metal electrodes that I showed on the previous slide to put it on an earpiece that has actually been molded to the ear of the person. So that's a very specific design here. Common mode rejection, we'll talk about it afterwards. And now if we look at the pictures very quick, so picture A, I just described it to you. Picture B is something that actually was just disclosed at the CES this year. So it's a company called Sleepwave, which is actually, I think, a spin-off of LG, if I'm not wrong, that have been doing sleep buds. So the picture is not very good, but what you can see, and when we actually tried them at the CES, they actually have 2 electrodes on each earbud, which is one in the ear wing and one in the ear tip. The exact same design as the one we use, so you're going to be able to see it a bit closer afterwards. And for that case, they actually use conductive polymer. So it's a good proof that conductive polymer actually gives you good enough signal to record EEG even with a single earpiece, so a very close distance between the electrodes. Picture C, again, the same group, ear EEG in Denmark, except on picture A, the earbud was actually molded to the person's ear. On picture C, it's a generic earpiece that they've been designing so that it could actually fit any type of ears. And picture D is a company called Emotive that released the M8 product. The M8 product in 2021. On those guys, you can see there are actually 3 electrodes on each earpiece, 2 behind the ear on the ear hook and 1 on the tip of the earbud. Again, using some polymers as well, but that also ensures quite a good stability of the electrodes as well. So now, coming to what we did, so we have actually a good picture of the earbuds we've developed. What we had to focus on, let's say the criteria we had to focus on were that we wanted to get something off the shelf regarding the materials that was cheap, biocompatible, comfortable, easy to clean, and that we actually molded ourselves. And we built the form factor we chose was actually this ear tip and ear wings. So it's two electrodes per earbud for now, because it actually ensures a good fit. And it also provides a decent distance between the electrode, so getting actually a pretty good signal even if the 2 electrodes are on the same ear. Regarding the number of electrodes, for our use cases right now, we don't need more than 1 channel, which is good because it would be difficult to fit 10 electrodes on an earbud like this. In the future, we might actually increase the number of channels if needed. Now, switching to the analog frontend. So what we call analog frontend, I think there are a few different definitions out there, but the one we're going to take here is that it's a component that does 2 things. First, amplify the differential signal captured by the electrodes, and then also sample it along the time axis and digitize it along the, digitizes the amplitude of the signal. Again, what are the constraints that we need to look at when we choose this analog frontend? We need to, again, maximize the signal-to-noise ratio is the goal here. So there is a characteristic of those amplifiers that is called the common mode rejection ratio. This is basically their ability to cancel the signal that is present in all electrodes that are recording on your body, opposite to differential signal. And also the signal resolution is key here because, of course, if you want to have a good prediction algorithm running on it and a good signal processing, if you encode your signals on 2 bits, it's probably not going to be enough. But this is also to take as a trade-off, because if you increase the resolution, as we're going to see, it can have impacts on memory and CPU and battery consumption.
Can you share how many bits your A to D converter has?
Sorry, can you say that again?
Can you share what is the resolution of your A to D converter? 16 or 24?
So we've used both. Actually, we can go below 16. We've been doing trials below 16 and we still get pretty good results. This is part of the optimizations we do. It's kind of finding the best resolution that fits our needs. I think it's not going to be the same if you do EEG, EMG, EOG. It can vary a lot depending on your application.
Thank you.
And again, cost is also a big issue. Not a big constraint for us. We don't want to take a component that costs like $100 for sure. We are not hardware maker in that sense. We don't build the analog front end, so we use off-the-shelf components and work with some providers also to have some design, some custom designs at some time. Regarding the size, since we want to fit small earbuds, it's already super packed in those earpieces. We definitely want to have it as small as possible. And yeah, the memory and battery consumption, as I was saying, it's good to be able to sample at a very high sampling frequency and have a very high resolution, but it has definitely a big impact in terms of memory and battery consumptions when you then run your signal processing and machine learning algorithms on it. State of the art. I just want to zoom a little bit on 2 criteria to pick the amplifier that are very important. First of all is the input impedance. So I tried to summarize the equations here, but I'm not going to go through them now. You can have a look later if you want. What's important to notice is that the common mode rejection ratio varies the same way as the input impedance of the amplifier divided by the difference of input impedance of the electrode difference of electrode skin impedance. This is what we call the potential divider effect, and actually we don't control the difference between the impedance of the electrodes that much. So it's something that we don't have much control on. We know that it's usually more than 10% and can go up to 50% sometimes, so it's pretty huge. So it's really something that we need to have in mind when picking the amplifier, is try to estimate how big that difference can be in terms of ohms, and pick an amplifier that has a high enough input impedance to make sure that our CMRR is high enough. And the second thing that is often overlooked is the impact of the current noise. So the current noise is the noise that's going to go through the electrode skin impedance of each of the electrodes. Usually it's negligible, but it's just something you need to keep in mind, because if there is too high of a current noise and it goes, and then you actually have electrodes that have very high input impedance, which is the case when you use polymer electrodes or like conductive polymer electrodes, the same as we do, then you need to pick carefully the amplifier to make sure the current noise is low enough so that when you actually multiply this current noise by the input impedance of the electrodes, you don't get something, let's say, above a microvolt, because above that you're quite sure that you're going to pollute the EEG signal quite a lot. Finally, the selection of the ADC. There are like different architectures out there. The two, let's say, most famous ones are the SAR, successive approximation, and the delta sigma. We're not experts in that field. I think Texas Instruments is doing a pretty good job at explaining you what works best for your use case. I just put here a quick screenshot of one of their guiding table to make your choice. But again, I think like you just need to fit your needs regarding those dimensions. And again, finding the optimal resolution for your application is pretty key if you don't want to waste computation power. Sorry, here we cannot really tell you what we did. One of the boxes, there are not going to be too many of them, I promise. But here, actually, we have confidentiality agreements that we cannot really share on that part. Now, final topic on the hardware side, the EMI. So as you already know, there is a lot of noise, of electromagnetic noise affecting your system. Power line noise is one, but there are also capacitive effects and inductive effects. And we're just going to see quickly the strategies that we have to cope with those different noises. So the state of the art in terms of shielding. So I quoted here a very nice paper that is actually digging into all the different types of shielding you can do. Usually when we think shielding, we just think just put a metal cover, like a metal shield around your wire. It's actually a bit more complicated than that. You could leave the potential of that shield floating. That usually doesn't work that well. And then if you apply a potential to that shield, there are actually several ways to do it. You could put like the ground. You can use the inverted common mode, which we also call the bias here. Or you could use the same potential, which we call active, which actually they call active shielding. The graphs on the right show you the differences between all those different approaches. It's not always super different, but it's true that even in the experience we've been doing, shielding with the same potential actually improves a little bit the quality of the signal. The reason being that it cancels any kind of capacitive effects you could have between the shield and the wire that is going through the shield. So very nice paper. I invite you to read it if you don't know it already. And the grounding. So the grounding, funnily enough, is something that is often quite overlooked when designing the hardware on the devices we've been trying. It's okay to leave the ground of the system floating in most cases, and sometimes it's not. And when it's not, you want to make sure that you bring the ground as close as possible to the common mode or to the potential of your body. One way to do it is to simply connect the ground to your body, which works pretty well. The only thing is that it's going to leave usually quite a high impedance between your body and the ground. So it's not going to, there's still going to be a command mode potential that is going to be significant. A way to cope with that is called driven right leg. I think it's quite a well-known technique. The idea is to capture the command mode, revert it, use an op amp to inject it back to the body. From a physical standpoint, there are many ways to interpret this. From a theoretical standpoint, I think a good way to see this is that it's actually the equivalent of reducing the impedance that connects the body to the ground. And so this way, bringing the command mode closer to zero. So something that has been actually quite useful, not always necessary, to be honest. A lot of devices out there don't have a driven right leg, even not the ground. But if you want to be really robust to any kind of EM noise, generating a strong, if you want to be robust in a very strong noise environment, then it becomes a kind of mandatory. And regarding the inductive effects of the magnetic field, that one is actually pretty easy. If you have a loop made by a wire and magnetic field goes through it, it's going to create inductive currents. Actually, a nice way to get rid of it when you have wires, again, it happens only when you really have wires, is to twist them. Very easy to cancel the magnetic field. And also finally, having a large PCB ground plane also helps, especially if you have like several components connected to it. It helps getting rid of the spikes and kind of small artifacts that you can have generated by one single component, because it can capture more charges. And so what we did, so the two pictures we have here are the first demo kit we used to have in 2021. That was still the wired version, wired in the sense that the electrodes had to use a wire to connect to the amplifier, to the analog front end. Now we switched to something that either has just a wire between the two earbuds, or just no wires at all. And the techniques we put in place, or as I was mentioning, the active shielding. Every time there's a wire, we use active shielding. Driven right leg, it's done for the wired versions. On the single ear version, we don't have yet that implemented. It's part of the plan of what we're going to do in the coming months. Twisting the cables we did on the old prototype. It's not useful on the new prototype, and the large PCB ground plane is actually just a good practice of electronics. Any questions so far that I would have missed?
Not in the chat.
Okay, I'll keep going, and you tell me if there are any questions. So right now what we're going to do is we're going to first of all show you and then explain to you the controls we've developed. So there are 9 controls total, 3 controls based on EMG activity. So it's actually the EMG coming from your masseter muscles, so the muscles that are responsible for clenching your jaw, either 1 time, 2 times, or 3 times. This is a control, I mean, those are controls that we brought to what we call the product stage, in a sense that it's robust to any kind of environment, any kind of activity, and it also works on pretty much everybody we've tried on so far. So it's really something that is already ready to be implemented in an existing product on the market. And recently, we also developed 6 EOG controls, basically combinations of eye movements from left, right, and center. This is still at the demo stage. So again, we're following the same steps as for the EMG controls, which is much more early in the process. And so yeah, we plan on putting them, bringing them to the product stage is a part of the roadmap we have for this year. Maybe a question, do you prefer to do the demos now or to wait until the...
There is a question on the chat. Are controls robust across the individuals? Do you have a calibration sequence?
No, so I was going to talk about it afterwards. Something that we're quite proud of is that we don't need any calibration. The first reason is that in terms of UX, calibration is always painful for the user, so it's something that we wanted to avoid in the first place. And in the way we've designed the algorithms and let's say the data collection phase that we did, we managed to get diverse enough data so that calibration is not required. This being said, calibration is still kind of our joker card, if you want. If we really want to push the performance for a given user to a level that is above what we already have, then we can use a specific calibration.
Tom, you raised hand. Feel free to ask your question.
Thanks. Thanks for sharing all this information. It's been really interesting. Looking at the form factor, it seems like it's a closed headset. Is that correct? That's a closed ear headphone?
It's an in-ear earphone.
But it's closed, correct? Like you can't hear things necessarily through it?
You know, it's a seal. I mean, like the regular earbuds, like those AirPods and what you would find on the market. Yes.
Okay. Yeah, I ask. I'm wondering about, we're pointing towards some people. You show the HoloLens, and a lot of people in that are first-line workers working in scenarios where they need to hear people around them, and closing off that channel of hearing is potentially solvable, obviously through pass-through, right, or even open-channeled headphones, or in the reverse situations where you need PPE for protecting your hearing. I wonder if you have thought about any of those use cases and acceptability for those first-line workers where PPE is required and they need to have some sort of noise blockers in their ear, where maybe these could be such things, or in situations where they need to hear those around them and don't want the headphones to block their hearing channels.
So I can let Yacine answer the use case. I mean, the question from a use case perspective. Let's say from a technical perspective, we can do both in a sense that all we need really is a contact of the electrode with the skin. So right now we have this kind of ear tip that goes all the way through your ear canal. If we were to do a circle that would just fit around, for example, your ear canal or the entrance of your ear canal, that would give us the same results. So it's really just a matter of choosing the reference, the design we want to go with.
Awesome. Yeah, thank you for sharing.
Yeah, from a use case standpoint, I think both exist, as you were mentioning. There's going to be the case where you actually have to have industrial worker, frontline workers having transparency or not being obstructed on their ears, and you're going to have the other way around, which is having people that need hearing protections. I think for us, and that's what we're trying to qualify right now. I would see this as being two product lines in the longer run. I think what we're really trying to assess right now is where really we can add the most value. And what we're seeing is that usually the one that have hearing protections work in environments that are the harshest, and where if we get back to solving a real problem, that was the key point at the beginning, this is where we'll most likely be the most valuable of our first product. So that's why we're really focusing with closed earphones or closed form factors at the moment, because we think this is going to be very likely the first design of our first product line. It doesn't mean we're not going to go with an open ear kind of approach afterwards, but the very first product line will very likely be a closed ear.
There is another question in the chat. Can you distinguish forehead and jaw EMG?
What was the first one?
Can you distinguish a forehead and jaw EMG? So when you move your forehead and when you move your jaw.
When you okay, how do you move your forehead? Just to make sure.
Your brows, I guess.
Yeah, eyebrows, I think.
Okay, eyebrows. Yes, yeah. The signature of the jaw muscles is pretty outstanding, I would say. So we don't confuse it with other muscles.
Thanks. Okay, go ahead.
Good.
So just to follow up on that, hi, Teresa Nick. I'm just curious. So basically, you're just recording the jaw muscle. You're not trying to kind of parse out other muscles for potential kind of future applications.
So we are. Let's say we had to start somewhere, and it's a combination of the signal you can pick the most easily and the use cases that the best use cases for the users in the end. So that's kind of how we evolve. We have a list of all different signals we can pick, how easy it is to get them, how much data we need to train our algorithms, and on the other side, from a user perspective, how gentle a gesture it is, how how much it gets accepted, how much the user needs to train on it. Those are the kind of signals we use to classify, to rank the gestures that we want to go with first.
Maybe to add on to that. Oh, sorry, go ahead, please.
Oh, I was just going to say, yeah, it's nice work. Yeah, it probably is going to be easier to distinguish the EOG, from jaw than the forehead. But yeah, really nice. Thanks.
So yeah, to iterate on that, I think as Alain was saying, like there's been a bunch of different EMG or muscular activity that we've been looking into. We're not fully done in that. I think one of the key expectations that the users had on what we're building is beyond high speed privacy, right? And I think one of the cool things with like the jaw muscle is like you can't see it. I mean, I'm gonna give you a quick demo in a sec, but like it's barely noticeable except if you really know that I'm doing it and you're really focusing on me. Any other gestures that we've looked at, except maybe tongue motion, but that's another topic. Except every other gesture that we've been looking at would require some kind of facial expression, and in that sense would be less private than what you would have with the jaw clenching. So that's one of the reasons we started there as well, beyond the technical aspects and the user adoption.
Can I add to that? So it's the jaw muscles, of course, keep that privacy. That's the good part about this kind of application. But on the other hand, because it's private, people tend to fidget a lot with the jaw muscles. I wonder, the same way you fidget slightly with your leg, no one can really see it right down there. So I wonder if you've had this kind of challenges with these type of fidgeting type of motions that happen internally in someone's mouth or jaw.
To be transparent, so this is something we're investigating. We're going to be investigating from a user standpoint. Like as we said, we're talking about dog fooding earlier, right? So we're trying to use these pretty much every day, a couple of like half an hour a day. We haven't observed this on the user population that we are at the moment. Definitely before we release anything in the nature, we're going to make sure that this kind of behaviors have been observed. I think, again, getting back to the pain point you're trying to solve, right? In some of the discussions we've had today with like industrial companies, it happens that, for instance, they're going to be using their fingers so much to press on buttons that they're going to have blisters at the end of the day. So I think there's also like kind of this trade-off between like how painful the current gestures are for you versus like what kind of like less painful our gestures would be for the user. And I think if you think about keyboards, it's kind of the same. We all have carpal tunnels. So like these things are great. They're very high input, but in the end they leave like some kind of issues on the body of the user. So we're going to try to get rid of this as much as we can. Of course, we won't release anything that would be an issue for the user, but definitely what we're seeing is that the inputs as they exist today are not perfect and far from perfect. So we're just going to try to at least first reduce that kind of penability for the user.
When you say you use jaw clench, do you mean you can distinguish the two sides, like left side versus right side?
That's a perfect question that we have and that we've been testing internally. We can differentiate it, but the issue is that not everyone can actually differentiate it. Like I can do it. I think we have a few people in the office who can. We've had a few people during our product testing who can do that. But so we haven't built so far the ability to say clenching right, clenching left. If it happens that I'm wrong and that 99% of the population can do it, and then just the one exception, then of course we'll implement it. But at the moment, we've just created one single gesture.
So, more questions? Okay.
Cool.
Wow, demos.
So Alain, if you just want to cover while I'm setting up the first demo.
Sure. So first demo, Yacine is actually going to use the earbuds to control the slides of this presentation, I guess, without using his hands or his voice. It's kind of the magic effect that we use usually. Again, you're going to see it's pretty robust. So there was a question about what happens when you are chewing, I think. Also, we've trained the algorithm to be robust to pretty much any kind of potential artifacts we've been encountering so far. So, for example, you could actually chew a gum; it would not trigger the controls. So again, that's what I was saying when I was mentioning that this is at the product level. So we kind of identified most of the corner cases. There's always going to be more, but it's already, I would say, like 95% covered. So yeah, pretty robust. Again, we've been testing it also with like many people, and it's just a matter. I mean, usually it works pretty instantly, and for the people for whom it doesn't work at first, it's just a matter of a few minutes to catch up and to catch really the gesture and how it should be done.
Yeah. So just to show you, so right now I'm using the clicker. I don't know if everyone sees me. Going to change the slides. Going to change the slides. Going to come back. Going to come back. Now I'm going to drop the clicker. Right. I'm going to go to the next slide. Going to the next slide again. Going back to the previous slide. Going back to the previous slide. Right. So this is just using jaw activity that we've mapped to going to the next slide, going to the previous slide. As you can see, I'm talking right now. Nothing happens. I could actually drink some water and nothing should happen. So nothing happened. I think there was a question about forehead motion. I'm going to try to move my eyebrows like this. No false positive, as you can see. I could be running around the room, but you would not hear me. But honestly, it would not.
Oh, they will. The microphones are.
Oh, okay. So I mean, I can be running around the room and nothing happens, right? So really, we've trained it like to a lot of different things. I've just realized I forgot my gums, which is usually the Wahoo effect at the end of these. So that's what Alain was mentioning as having like a product-ready version of it. And I think I don't know if you mentioned it, but like everything's running on the device, right? So there is no processing happening on the laptop as we speak. So the goal is really to make this as private as possible, so no data leakage, but also as fast as possible. And so running it on the device prevents you from having to go through any kind of external processing unit that would get the signal, like run it and then send back the information. Yeah.
Question, how steep is the learning curve? I guess when you put them on, you cannot instantly control it. How quickly people learn the gestures, and do you have some adaptiveness on the other side, or you count on the human's adaptiveness?
Yeah. So, there's always some adaptiveness, right? That's needed. It's like again, getting back to the keyboard and mouse. It's not natural if you think about it. Like you have to train for it. But that's the perfect question. What you're asking, and this is the product part that we're trying to solve. It's still an ongoing, let's say, work. But right now, we've managed to get to a tutorial that takes less than 1 minute to complete, and that teaches the user the gestures. So both the double and the triple clenching that I'm displaying right now in less than 1 minute. And we get something like 80% of the people who onboard autonomously using that tutorial. And for the others, we have to intervene. I mean, like go with them, show them usually the raw signal or the filter signal so that they can really see what's happening when they're doing the gestures and get some kind of visual feedback. But we are working on it. Like the goal is really to get this like a, same as, box opening user experience when you open your Airpods for the first time and you get to like kind of these few steps that enable you to use them right away. And we want to get to something that is as small as that. I don't know if that answers the question. Yeah? Cool. All right, I'm going to go to the next demo and I will let you just present it while I prepare the thing.
I think there's a hand raised.
Oh, sorry, my bad. Go ahead.
Hi.
Hi, home.
Hi. Hey, sorry. So I have a question. So it looks like you're trying to use some functions of our body that's not designed for these things. I wonder if you use your jaw muscle for all kinds of different purposes, is putting stress on our body. It's going to wear us out faster because our jaws are designed for special purposes. So I wondered if you had any thoughts along that line.
So I'm going to answer in two ways. I think the first question is like, what's been designed as a natural way to use our body? Like, for instance, is moving my hand to my earpiece and pressing 2 times a natural way to use my body? And I think that for most of it is just like the evolution of what we've trained humans to do, but there's nothing natural in having to go there and like press a button to control something that is actually in my ear, right? And so if you think about it, like the fact that I have to enter the letters, I don't know, like B-A-N-A, banana, on my keyboard to transfer the banana idea to my laptop is not natural as well, right? I would just like to kind of transfer that idea some like with another manner. So I think the natural aspect of it for me is always like kind of something I challenge a little bit. Now to get to your point, it's like what really matters is like what's the user feeling when they use these gestures for controlling their device. And that's something we're tracking very closely. So right now, when we are doing this kind of product testing in our location, what we're really following is like, okay, is it easy to use? And is it simple to use? Sorry, is it easy to use? And is it like intuitive? Like as in, would you use that to control your device if you were put in the situation where you have that situational disability that we were talking about earlier? So if you're running, if you're carrying something. The easiness, we are above 92% right now of the people, and we keep working on it to have like, to be able to reduce the gesture to something that's subtler and subtler. The intuitiveness, we're above 85% of the people who say like, yeah, we've been putting them in situations where they have to carry something and someone calls them and so on. And the question is like, would you prefer to drop it or would you prefer to use what we're doing? And so usually what we do realize is that they're actually able, I mean, most of them say, okay, I think I see the value of it, me not dropping my stuff, like whatever, putting out my phone and just using your controls. So that's kind of more what we're going to be tracking. The long-term effects of, is it like wearing your teeth faster than what they should do, for instance? I think this part we're not too worried about, as long as we're talking about like your regular usage, like how many times a day or an hour are you pressing a button on your earpiece? It's going to be like maybe once an hour, twice an hour max. It's going to be always lower than you chewing a gum, you eating, or you doing anything else that's actually using your jaw muscle during the day. So of course, the usage of like these controls cannot be applied to everything. Like an action that you would need to repeat, like typing on a keyboard, would not be perfect. But for a click or like a button that would be usually placed on your earpiece, we think that this is a good replacement at the moment. Again, it's always a matter of like what's the context you're using it in. Does that make sense? Or
thanks. Thank you.
Thank you. Any other questions?
Let's see.
Good. So Alan, I will let you just do the cover while I set up the next demo.
Sure.
Please.
So this demo, as I was saying, is based on EOG activity. So we designed for now 6 controls based on eye movements. Right now, the movements that Yacine is going to use are either moving your eyes once to the right, twice to the right, or to the right, then all the way to the left and back in the center, and the opposite starting on the left side. The EOG, maybe a quick recap on how it works. I don't know if everybody is like totally familiar with that. Actually, what happens is that there is a consistent potential difference between your cornea and your retina. So basically, your eyes are like 2 electrical dipoles, and whenever they move either left to right, up, down, etc., it creates a local electromagnetic field, and this gets the surrounding particles, the surrounding ions to move. And again, then it actually works the same way as EMG and EEG. It travels all across your head, all the way to your skin.
And
so,
I think I'm going to be ready whenever you want. Just going to switch the screen.
Okay. If I'm not wrong, Yacine, you're going to use the Spotify demo? Is that
yes,
right?
I'm going to use Spotify, exactly.
So basically what he's going to do is he's going to like play, pause, skip the music, add to favorite, a few different kind of controls. Again, keep in mind, this is something we issued right before CES, so end of 2022. So still at the demo stage, definitely not as robust yet as what you have seen on the EMG side, but we're going to be working on it in the beginning of 2023.
All right. So yeah, as Alain was saying, what I have in front of me. So of course, no camera is involved. Okay, everything that's happening is happening with just my eye motion. So and just by the sensors placed on the earphones in my eye motion. So what I'm going to do at first, just to show you hands-free, I'm going to just open the menu. All right, close the menu. All right, I'm going to pause the music now. Okay, go to the next song. Go to the next song again. Okay, put it in favorite mode. Remove it from the favorite. Okay, pause the music again. Okay, play the music. Okay, go to the next song. And go to the previous song. Okay. That's basically kind of, as you said, like we're still like, there's a bit of try and learn, but that's kind of the very basic we've been putting on these controls. The demo is on Spotify. That's not necessarily the best use cases. It's just like, that was the simplest one we could develop, but ideally tomorrow, we're thinking about using this as a way to navigate through an app menu or having some quick controls like, answer or reject a call or whatever, like 3-4 options. Sorry, just gonna stop it. On AR glasses. And so, as you can, I don't know if you saw my eyes, but so basically the motions are like going to the right, going to the left, doing some wipers, left, right, center, right, left, center. Right now, at the moment, we do have to push them a bit to the edges of the eyes because this is what provides the best signal-to-noise ratio. One of the key things we're going to be working in the next few months is actually reducing the amplitude that's needed, so you can have very subtle gestures of your eyes to control the same kind of things, and also like so really reducing the amplitude so that the gesture becomes much more natural. And the last part is that we have a lot of different candidates on potential eyes gestures. One of the things we'll need to do is do the same product investigation that we did for the muscular gestures, where we actually had a lot of different ones, and we reduced it to a list of like 2 or 3 that are the most relevant for users. So that's going to be the kind of next steps, reducing the amplitude that's needed and doing more product investigation to really select the eyes controls that are the most relevant for the users. Does that make sense? Yeah. Any questions here?
Yes, there is one raised.
Yep. Go ahead now.
Hey guys, cool demo. Thanks for sharing. Is there like a trigger to make it start listening? Is it an always listening state? I'm wondering about noise in the environment. If you're using, if you're reading or like looking around your environment, what that false activation might be, things like that.
So the way we see those controls, the EMG controls we've seen before, they can be used, especially the double and triple clenching, they are meant to be used in any kind of environment. So you have your earbuds, you're like in the street or whatever, you can like trigger anytime you want, and it's being listened all the time. Regarding the EOG controls and also the single jaw clenching, the goal we have is really to make them available in a contextualized environment. Because of course, your eyes, you use them for a lot of different things, and you don't those EOG controls to be activated when you're just like walking in the street and looking all around. But if, for example, you're browsing your HoloLens menu and you want to browse the different tiles, you know that as a nominal use case, the gaze is going to be centered to what's in front of it. So it actually unlocks those controls to be used in that contextualized way.
Hey, come, go ahead. You don't have to wait for.
All right. Here's some ideas.
Please.
I wonder if you have thought about. So listening to this, I was very excited to think about an application. For example, a car. I'm driving a car, and you are monitoring my eye gaze and everything, and maybe some, I don't know, some signals, and you realize I'm falling asleep. And then you could, I'm not necessarily controlling anything with these muscles, but you can give me a warning saying, hey, wake up, you're falling asleep. Or I have a certain medical condition. Let's say a combination of muscle twitch, heartbeat, and some kind of a signal elsewhere. A combination of those is a kind of precursor of some kind of a condition. And then you can give me some kind of warning. Is anybody doing anything like that? Are you guys thinking about anything like that?
So so these are 2 very good use cases. And then funnily enough, on the eyes activity, you do see. So again, like nothing that we've built into a model or any kind of predictive state you said, but like
The tiredness, you can definitely see it on the EOG signal. I remember because like to train that algorithm, we did a few recording sessions at our office, right? And I'm traveling a bit. And so basically when I was super tired from traveling, like a shitload of jet lag and so on, and I was doing these recording sessions, Claire, who's been like spearheading the product, was like, are you falling asleep right now? And I'm like, yeah, shit, I need to wake up. So basically, yes, you can see an impact of being tired onto the EOG signal. And interestingly enough, we were talking about this earlier, but there's a project I think that you guys have been working with the MIT lab called Attentive View that is building some glasses that are meant to detect, among other things, if the user has some kind of drowsiness. There's another company in Japan that's building glasses with the same kind of purpose. So yes, definitely this is a good idea. And this is one of the applications that could be definitely done to like put this technology to another use than just controlling stuff. All right.
Thank you.
Sure.
Question.
Yes, please.
Is there any difference between in-ear electrode versus around ear? Do you compare the signal noise ratio, for instance?
For EOG specifically or for anything else?
For jaw plunge or EOG?
Alan, did you get the question or do you want me to repeat it? Okay.
Yeah, I got it. So the nature of the signal is the same. The only thing that changes is the distance between the electrodes. So that's really the main factor in terms of SNR. So if you're around the ear, you may actually find some angles where the distance between the electrodes is actually a bit higher than what you can have only within the ear.
Thank you.
Good. Yeah.
Just to follow up, that's a good thing, right? We want the distance to be further away. Alan, you mentioned in the one setup, the distance of the electrode is further away, and that's a good thing. That's a desirable.
Yes. So basically, the way you can see this is like if you imagine that the origin of the phenomenon is somewhere in your head, and you have like two electrodes. You want the angle that is made between those two electrodes and the origin of the phenomenon to be as wide as possible. That's pretty much the rule of thumb. So by putting two electrodes in the ear, for example, you can have a very good look at what's happening in the brain close to the ear. If you're looking at what's happening in the frontal cortex, for instance, it gets a bit more difficult. Does that make sense?
Yep, thank you.
More questions from the audience here, from the remote attendees?
Alan, back to you.
Okay. So I'm going to jump on the software part. Maybe we'll go a bit less into the details here, but if you have questions, feel free to ask, and I'll see how much I can share on those topics. So summary quickly, in a nutshell, everything we do runs on the device. As Yacine was mentioning, it all runs on the MCU. Several advantages. First of all, privacy. No personal data leaves the device. And also in terms of integration, it kind of speeds up the process or makes it way easier. Think about it like if we were just streaming data to any kind of a recipient device, they would have to run on the algorithms on the device itself. We'd like to provide a very detailed SDK. Right now, basically our device just sends you 1, 2, 3, 4, 5, 6, 7, 8, 9, depending on the controls that we triggered. And so it's either a very simple integration on the recipient device side, or for some cases, we may actually want to be integrated directly into some existing Bluetooth profiles, especially the ones that, for example, are used to control the music, right? In that case, we are quite agnostic of who is plugged on your earbuds, and we can just play pause the music on any kind of device seamlessly. The specs of the chip we have, not that important, but just to show that it's a very constrained environment. So it's an ARM Cortex M4 MCU, but again, we are not tied to it. CPU is just 64 megahertz, and the RAM available on what we have today is 64 kilobytes, but we actually use much less than that because we need to put the Bluetooth and everything else on the same MCU. So first point was the data. So again, I'm probably, let me know if you have questions. I can dig a bit into more details here, but just going to summarize a little bit what we figured was the most important during our journey into like starting from zero data to have a very good model. And so, of course, the data collection part is key, and especially if you want to be able to build an algorithm that is calibration free, as we do, and that works on anybody, you need to have a massive subjects diversity and also environment diversity, right? To be robust to any kind of noise, you need to make sure that you are able to actually depict, that your model is able to depict those noises very clearly. Data collection is always not, often not sufficient in itself, and especially there are some quick wins to kind of add additional information without having to go through more data collection campaigns. Data augmentation is definitely the best way to do so. Two different ways that work pretty well. One is to add noise to the data, whether it's like white noise, pink noise, whatever. And also generating synthetic data actually proves to be pretty useful. It can be different ways. You can actually mix the signals that you've been recording. Also use some generative approaches like GANs or variational autoencoders, for instance. And finally, something that has also proven to be very useful is what we call active learning. So the overall principle of active learning is to learn of your mistakes and your uncertainties, right? So for example, one way to go through that is to pick the false predictions, whether it is from a user prompt or whether it is by manual review, relabel them and add them back in the training set. Or you can also do it like in a more proactive way and just say, I'm going to look at, for instance, the examples where the probabilities of the prediction is close to 50%, so our model is quite uncertain, and review those and label them manually, and then add them back in the training set. And this actually proves to be very useful, even with a quite small size of data that you have to relabel this way.
Maybe just to add a quick funny story on the data collection, because we've been spending a lot of time doing this in multiple environments. So we were at CES, right, 2 weeks ago. And so for those of you that know about electromagnetic noise, CES is kind of the worst place to be in. Like you have like Bluetooth, like modems, like very much, this is the worst place to be in. Maybe nuclear plant is slightly worse, but like you're very close to it. First of all, our demos work pretty well anywhere in CES. One of our new prototype wasn't working that well. And so we literally spent, I think, 1.5 hours just sitting on the ground doing some of the data recording with the new prototype at CES, surrounded by all these modems and so on, just to make sure that we would have the right amount of data to then retrain the algorithm later on. So that's kind of part of the environment diversity that you need to go through if you want to make sure that your algorithm is robust. Like whenever you spot something where you're clearly faulty, you need to make sure that you collect the right amount of data out there.
Second step, once you've collected all this data, is to perform the pre-processing. Again, the steps are quite common to any like signal processing and machine learning approach. So get the data, slice it into windows, filter the noise, remove the artifacts, remove the potential outliers, do scaling if needed. And I think something that is quite specific to what we've been doing is that those steps can be costly in terms of processing and also can affect very much the latency. And as we said, we want the latency to be as low as possible. It's already pretty low. We're actually working on making it even lower, like decreasing it by a factor 2 or 3. And so those are steps where you actually can win a lot of time by doing some optimizations. Same for the battery consumptions and same for the memory, of course. So optimizing those steps is quite at the core of having something that is a low computational footprint and low latency. In terms of the state of the art, just mentioning a few topics here of attention. When doing your filtering, again, there are different types of filters that one should keep in mind. They all have their qualities. They're like, I just mentioned here the FIR and the IIR filters, and the finite response, and the infinite response filters. Basically, some of those filters are just like a convolution that you pass on the signal itself, and that's the FIR filter. And the IIR is actually reusing the previous computation it has done in a recursive manner. So IIR is usually faster, but it's also non-zero phase in the sense that it distorts a little bit the signal. So you have to find some strategies to cope with it if you want to use them. So that's kind of the things that by like fine-tuning it helps you quite a lot reduce the footprint of your filtering. The artifacts removal, two main methods that have been quite tried and shown good results. The oldest one is the independent component analysis, quite famous. I won't go into it much more. But now people are switching more and more to just artifact subspace reconstruction. So this uses, in a nutshell, it uses covariance matrices as the basics of the computation. And even like there are some Riemannian geometry versions of it, where actually the distances that are computed are like geodesic distances or Riemannian distances, sorry. Distances between like symmetric positive matrix that are the covariance matrices. So it's some nice mathematics that has find a good applications into artifacts removal. Regarding the outlier removal, I think the main conclusion is that there's always going to be some manual review. You're never going to have one method that allows you to get rid of all the outliers at once. There are some unsupervised way to look at it that actually can help you speed up the process. Same things that we tended to use is high recall models, so building like very basic models to detect outliers based on some manual reviews, and just use it with a very high recall, so a lot of false positives, but at least instead of like reviewing 100% of your data sets, you can review like maybe just 10%, and that's already a huge gain that you can make.
Can I?
Oops, sorry, go ahead.
Yeah, can you talk a little bit about the difference between an artifact and an outlier? What do you consider to be an outlier?
Sure. So if you take a window of a couple of seconds of signal, you can have artifacts. For example, there was like a peak of EM noise, or you were doing a movement that you were not supposed to do. This is an artifact. It's something that you want to clean out of the signal because it's just adding noise in a way. An outlier is something that you recorded. But for example, you ask the user to do, I don't know, like a double clenching, and the user did it wrong and did a triple instead, or did something completely different. In that case, it's if you put it in your model, it's going to tend to teach a model the wrong approach. I mean, not teach the model the right shape of double clenching, for instance. So in that case, if you want to remove, you need to flag and remove those windows because they would decrease the performance.
So it's not a signal outlier, it's more like a mislabeling.
A trial outlier.
Yeah, it's something that because since we make the people do protocols, recording protocols, sometimes you can just do a wrong gesture.
Yeah, okay, thank you.
Yeah, I think I'm done with, okay.
Sorry.
Next steps, the model. Again, the way to split it is kind of finding the right architecture for the model, training it properly, and then performing some optimizations on it. The constraints we have in mind when we do it at Wisear is, first of all, as we said, calibration. We want to build a model that is, as much as possible, does not need any kind of calibration. Latency, we don't want to have like this massive neural network that takes ages to run. Same for memory, battery consumption, CPU usage. It's a bit redundant, but same as for the signal processing part, the machine learning part also can have a pretty strong footprint if you don't pay attention to it. Regarding the state of the art, so I just listed here the things that we tested and that gave, let's say, pretty good results or decent results. There are many. We spent a lot of time on it. That's actually the core. I mean, the core of the team is really data scientists, right? We're really a software company, signal processing and machine learning company per se. So this is what we started with and that we've been working on for 3 years now. Regarding the machine learning approaches, I think common spatial pattern is really like the basic of what is being done, especially with like helmets or headbands with many electrodes. Combined with classic ML models like SVM, LDA, whatever. And now there is also a big shift to Riemannian methods. So I already mentioned them for the artifact removal, but they are also pretty good in terms of of just pure like classifiers, and they win a lot of BCI competitions nowadays. So it's really a good algorithm to look at. Also, they're pretty fast in terms of both like training and inference. The only constraint I would say is that they work better if you have more electrodes at different locations, which is not really our case. But we've tried them and we have pretty good results as well. So again, still a very good candidate. Deep learning family, there are many different approaches. In terms of convolutional networks, there are tons of papers that describe like specific networks that they have been designing for EEG, EMG, like whatever. So there are many of them. And also quite a peculiar approach that we've seen recently is some image models. So already pre-trained image models being reused with spectrogram and scalogram, but considering them as an image. So basically taking this pre-trained model, adding a small data set and perform like transfer learning. So retraining the latest layers of the model based on those images of spectrogram or scalogram. In the recurrent neural network world, a lot of trials using LSTMs. Of course, like if you're using time series, it's very appealing to try to use those recurrent neural networks. There are decent results. Again, the research is probably not as extensive on those yet, but I mean, there are interesting approaches as well as eco-state network, another type of recurrent network. And finally, two other worth mentioning are the attention-based model, where actually, so in a nutshell, they would treat differently different parts of the signal you pass them as an input. And even more sophisticated is the transformer model, where actually the location, I mean, the model is going to learn by itself which part of the signal it should look at first, or with most importance. So again, those are models that come from other fields that have been used with pretty decent results using, I mean, for BCI approach. And finally, optimization, super important, especially for us. Those models, even once they are trained, they can always be optimized, meaning decreased in size and inference time and all that. Two common techniques are quantization, so trying to reduce the number of bits used to encode any weights of the model, and pruning, which is basically trying to the weights that are the closest to zero, trying just to put them at zero and see if it affects the performance, because this way you can actually save some space as well. Okay.
Done. All right. Thank you. Well, thank you very much for having us. I don't know if there are any other questions, but thank you, Ivan, also for the invitation. Really cool to be here and to discover all the great things that you guys have been doing, and also to let us present to you. So really appreciate it.
I'll be there next time.
Yeah. Any last questions from the audience in the lecture room or from the remote audience? If not, final round of applause. Thank you, Alan.
Thank you, Alan, for staying so late.
Thank you
so much, guys. My pleasure.